Welcome to this webinar on power electronics and motor control prototyping on CPU-FPGA target hardware with Simulink Real-Time. I'm Ethan Woodruff, an application engineer at the MathWorks, specializing in real-time simulation and testing. Joining me will be Brad Heeb, also an application engineer from the MathWorks, and Patrick Shank, an engineer at Speedgoat, an associate company of the MathWorks. In today's session, we'll discuss the concept of rapid prototyping and illustrate its use through an example of prototyping a motor control algorithm with the MathWorks real-time simulation and testing environment. Before we start working through our agenda, I'd like to show you right away the motor demo that we put together for you today. My expertise lies in the area of real-time simulation and testing and not so deeply in motor control, so I've invited my colleague Brad Heeb, who has more expertise in this area, to join us. He'll be showing us the demo and will also be around to answer questions later. At this point, we just want to give you a taste of where we'll be heading, and we'll look at each element in more detail later on. I'm going to pass the control of the screen over to Brad. So Brad, would you mind showing us the model you have put together, the hardware setup you're using, and maybe even run the model in real time?
Yeah, sure, Ethan. Be glad to help. So our goal today is to validate a motor control algorithm in real time using actual hardware. So on my screen, what you're seeing is the model we used to design our motor control algorithm, which is contained inside of this block here in the middle. We call this a subsystem. Connected to my algorithm model is a model of the plant. In this case, that consists of the inverter and the motor itself. And on this far right block, I have some scopes that I can use to monitor signals of interest. I've got one of those scopes open here. And finally, on the far left, I've got a subsystem which contains my basic test stimuli that I use to exercise my model. So, because we're in simulation, what we do a lot of is run experiments. So I'm going to run a test now. So I hit the run button, or the play button, some people call it. And what I'm doing is having the controller go through a startup sequence, which you can see on these scopes here. The controller is stepping through various operational modes. And as the simulation progresses, I programmed it so that at 2 seconds in, it's going to initiate a step response to go from 0 to 100 radians per second. So you should see that happening about now, and there it goes. And I'm looking to see, what my step response, rise time, settling time, those sort of things. And so, in fact, let me unobscure the signals, move the legend over a little bit, and yeah, looking at it, I'm happy with that result. I see all of my key performance requirements are being satisfied here on my step response. My motor control algorithm sequencing looks correct. The startup sequence is doing what I want. So in sum, I have confidence that it's working correctly in simulation, and now I want to see if it's going to work correctly on hardware. So what that means conceptually is I want to take this controller algorithm, which I have here, and get it downloaded onto my real-time computer over here so that I can actually talk to or drive the motor over here and the power electronics. And I'm going to do that with some specific I/O cards plugged into my real-time computer and then interconnected between the computer and the inverter with these cables here. So to make that happen, I'm going to show you another model. And so what I want you to notice is here in the center is the exact same controller model that we were using in simulation, but some differences are that I've deleted the plant model because I don't need them anymore, and replaced them with these orange blocks of colored orange, I guess, that are the I/O driver components that I need to connect the controller model here to the I/O cards in my real-time computer, and subsequently via these cables to the inverter and the motor. So to make this all work, what I'm going to do is hit this build button, and let's take a look at the progress window as it's running. And what's going on here is I'm converting the algorithm model into C code, and that code is being compiled and linked with the I/O driver code that comes with my rapid prototyping environment, and then that that collection is then converted into an executable and automatically downloaded via this Ethernet cable to my real-time computer. And as you can see, that process is completed and it's ready for me to interact with it. So what I'll do next is I'm going to open a script which will run a test. In fact, I'm going to run the same test that I just showed you in simulation. So let me fire that up. So what this script will do is it will set up data logging, initiate the test. As you can see, the motor is now starting to spin. Once the test is complete, it's going to collect that data, upload it again via this Ethernet cable over here to my host, and display it on a tool called Simulation Data Inspector, which is a data visualization tool that ships with Simulink. So I'm now ready to take a look at some of the data we had from our hardware run. First thing I'll look at is the rotor velocity trace, and here's what we just recorded from our hardware, and that looks very good. I'm happy with that result. I'm curious now to see how does this hardware test result compare with the simulation test result which we just ran. So let's go ahead and take a look. The simulation data was also stored in this same visualization tool. So I can scroll in here and find the same rotor velocity signal. I'll click on that, and I'll need to change colors here so we can, maybe blue would be good so we can see the differences. So now you can see that I have the two traces overlaid on each other. I'm not worried about the minor differences I'm seeing here in the startup transient. That's due to the fact that the rotor position in the hardware wasn't exactly aligned with the rotor position at time 0 with the simulation. So that's not of concern. What I do want to pay attention to is how it looks here on my rise time at my step response. And in fact, I'm seeing it looks very good here from this distance. Let's zoom in and have a closer look. And here you can begin to see that there are some slight differences between the controller response in simulation and hardware, but they're very close, very close. So I'm very pleased with the results that I'm observing here, and this has given me the confidence to progress this design and keep moving forward. So with that, I'm going to switch it back to Ethan, who's going to take you through where we're headed next with the rest of our presentation.
Thanks for that introduction, Brad. Now, using this picture, I want to go over all the hardware setup again, so as we're talking, you have a mental picture of how all the pieces fit together. Note, we have a laptop here with Simulink, where our models are. The models are built and downloaded to run on the target computer. Connected to the target computer are the power electronics, which drive the permanent magnet synchronous motor here. Now that you have that picture in your mind, let's go over the agenda. During the course of today's presentation, we'll look at these main topics. First, we'll briefly talk about what rapid control prototyping is. Then, we'll look at Simulink Real-Time running on Speedgoat hardware and how it permits you to test your algorithms in real time. Third, we'll look at a specific example in which we use Simulink Real-Time with Speedgoat hardware to interface our algorithm to brushless motor hardware. And then finally, we'll wrap up with the next steps you can take to try this technology out and to answer any questions that you might have. Today, you're going to hear us use the terms rapid prototyping and rapid control prototyping almost interchangeably. Rapid control prototyping, which is what our use case for this presentation is focused on, is an activity of real-time simulation and testing dealing with designing specifically control algorithms. Rapid prototyping is the more general term for any type of algorithm. So let's take a couple minutes and discuss what these activities are and how they relate to the software development process. The typical product development cycle proceeds from requirements, high-level design, software design, coding, followed by integration and verification and validation. Towards the start of your development cycle, systems and controls engineers model the system and design appropriate control laws through simulation. At some point, you'll need to introduce some hardware into the design to explore trade-offs or ensure that there are no neglected dynamics or to move the design closer to a product implementation. The goal here is to reduce the cost and length of your projects by finding control and system issues earlier on by testing the algorithms in real time and with real hardware. This is often called rapid prototyping. Typically, rapid prototyping takes place while the software and hardware teams are still not ready to provide a platform usable for quick algorithm testing. Another reason to use rapid prototyping might be to allow a controls team to work independently of downstream embedded development environments or teams, allowing engineers to save time, test new ideas, and innovate. Another application of real-time simulation and testing with Simulink Real-Time is in final controller validation testing. If the controlled physical system or plant is cumbersome, costly, or dangerous to operate, simulating it with a model running on a real-time target computer can reduce costs and time to market. This is referred to as hardware-in-loop simulation testing. But today, we're just going to focus on rapid prototyping, and specifically the case where we are dealing with a control algorithm, which would be rapid control prototyping. Here's a simplified conceptual view of rapid control prototyping. The goal is to run the Simulink controller algorithm design shown here as the green subsystem on the real-time target computer hardware interface to the actual plant hardware. Right now you can see that it is connected to the plant model, or in other words, the model of the thing we want to exercise control over, shown here as the yellow subsystem. This entire model was used to initially design the controller through the use of simulations in Simulink, but now we're ready to start doing rapid control prototyping. To implement this with Simulink is quite straightforward. We remove the plant model and replace it with blocks that represent the I/O interfaces to our actual plant hardware. In today's example, we'll be driving PWM signals out and reading analog and digital inputs from our permanent magnet synchronous motor. With the model configured correctly, we'll press this button here, right there, to start the build process. During this process, the code generator will generate code from the entire model, test vectors, controller algorithm, I/O blocks, and verification checks. It'll then initiate the compile and linking specific to our real-time simulation and testing environment. Once that has finished, it will download the resulting real-time application onto the target computer hardware, which is running a commercial-grade, optimized real-time kernel. Now, we are set up to run the same test that we ran on the desktop simulation with the actual plant hardware at natural operating frequencies, speeds, and timing. So that, in short, is rapid control prototyping, an intermediate step in the development cycle between control law design and embedded implementation. I quickly want to point out two examples from customers using rapid control prototyping and how this sped up their development. This first one comes from Wind Technologies. Wind Technology designs drivetrains for wind turbines. They recognize the power of simulation to design control loops for an inherently unstable machine. But they wanted to extend that way of working into the real-time world by rapidly prototyping and modifying those control loops. They were able to specifically do that through the use of Simulink Real-Time and Speedgoat hardware. In the end, because it was easy to go from desktop simulation to the real world, significant time savings and higher reliability were achieved. This next example is not a power electronics example, but also shows how rapid control prototyping can help in other applications. The Eranik R5 unmanned aerial system provides cinematographers with a camera motion system for close-range aerial filming. With a top speed of 80 miles per hour, a camera payload of 18 pounds, and a GPS system accurate to within 1 inch, the R5 is designed to deliver performance, safety, and ease of use. In preparation for flight tests, they generated code from the controller model, which they compiled and deployed onto an onboard real-time target computer running Simulink Real-Time. In some cases, the team was able to accelerate development iterations by updating the model and generating new code in the field between the flights. Now that we understand what rapid control prototyping is, and even seen a couple examples where it has been employed using Simulink Real-Time with Speedgoat hardware, we should take a moment to explain what Simulink Real-Time and the Speedgoat hardware are. Simulink Real-Time is one part of a two-part real-time simulation and testing solution. It is the software technology and environment portion provided by the MathWorks, which recreates a Simulink experience in real time with the physical world. The real-time target computer and associated hardware is the second part of this solution, and it comes from Speedgoat. Patrick will provide some information on the hardware in a few moments. But before he does that, I'm going to tell you a bit more about the capabilities of the software technology. It is also important to point out that the Simulink Real-Time environment is a two-computer environment. There is your development computer, which hosts your MATLAB, Simulink, and Simulink Real-Time software, and where you create your models. And then there is the real-time target computer, which operates under a commercial-grade, multi-core, multitasking real-time kernel that comes with the Simulink Real-Time license. The two computers communicate via a standard Ethernet connection. Through this connection, the built real-time application of your model is downloaded from the development computer onto the target computer, ready to start testing. This two-computer setup allows greater speeds and determinism for your real-time application. With simulation and testing, interaction is everything, and Simulink Real-Time provides many options. You have access and control of your real-time application's execution, parameters, and signals during runtime directly from within your Simulink and/or MATLAB windows. You can also log your signals in the target RAM or on its disk for later retrieval, analysis, or visualization seamlessly into MATLAB. You can interact with custom UIs that you design with the Simulink Real-Time Explorer, MATLAB, or other programming environments supported by our extensive APIs. Lastly, the environment is open and extensible, making it possible to interface to all types of software. So in summary, Simulink Real-Time is an environment that lets you quickly configure and use your MATLAB Simulink host with your real-time target computer to create real-time applications. We are actively working to add additional functionality important to those that are testing in real time, making it more flexible for all sorts of applications and extending its interaction with other MathWorks tools. Now, before I hand you off to Patrick to discuss more about the hardware element, let me give you a taste of Simulink Real-Time with a simple demonstration. What I have here is just a simple example model that I'm going to use to demonstrate the Simulink Real-Time environment. What this model does is take a square wave produced by the signal generator and add oscillations on top of it. So let's see that real quick. Alright, it should be done. And as you can see, the purple square wave come from the signal generator has indeed oscillations on top of it, denoted by the yellow line in the scope. Now what I want to do is to take this model, configure it for real time, build it, and then download it to my mobile target. To configure that, I go to the model configuration parameters. In the solvers, I want to change this to run infinitely until I tell it to stop. I need to pick a fixed step solver. In code generation, I need to pick the Simulink Real-Time system target file. Hit apply, and that is as simple as that. Those three parameters are all I needed to do to configure my model for real time. So now let's build it. Okay, we can watch the build process. Right now it is generating the C and H files. Initiating the compiling of the C and H files. When it finishes this, it will then do the linking and scroll back up here real fast. You'll see it created our real-time application and then downloaded it directly to our mobile target, which you probably saw the screen update when it did that. Alright, so I can put this into external mode, which is a connect, which now takes the model offline from the Simulink engine and then connects it directly to the real-time application. Push play, and you can see on our target screen that we do have a waveform. This block represents that scope that you see on the target screen. If I change this parameter here, you should be able to see that it dampens out that oscillation, and indeed it does. I can also see this on the scope here. Pull that over there, pull this back up. If I change this, you can see that we're applying those in real time. All right. Now, I want to take a quick moment to show how I can add some I/O capability to this model. In my personal library here, I have a couple blocks I'm going to pull in. All right. What I'm going to do is, as I'm talking here, hook up a I/O block which actually is going to drive this LED. So we'll be able to see it blink with the signal generator. The reason why I added this rate transition block is because the model's running pretty fast, but I don't need to sample that signal generator signal that fast. So I'm going to put 0.04 seconds. All right. Now that I've added those blocks, let's rebuild. Okay. Connect. Push play. And you should see we do have a blinking LED right there. Now I can go into the signal generator, slow that down a little bit, make that 1, and when I hit apply, you should see that LEDs blink a little bit slower. We'll stop the model now. And I do want to show you that I can also pull back data directly into MATLAB. I was logging data to the buffer using this output port. So let me show you that real fast. When I built the application, we created a variable called TG in our workspace. That gives us access, programmatic access, to our real-time application and the execution running on our mobile target. So what I'm going to do now is I'm going to get some data. You can see here that I have some data in my time log as well as my output log. So I'm going to go time equals tg.timelog and data equals tg.outputlog. Now that I pulled that data into MATLAB, I can plot it. You can see our plot right here. You'll also note that there is just the last 6 seconds of the data, which is because it's an adjustable circular buffer. And when we zoom in, we can see the oscillation on top of our square wave. Now that we have this in MATLAB, we can do a lot of stuff with the data, which allows us to take advantage of all of our toolboxes as well. All right, well, I hope you enjoyed this quick little demonstration, and we'll go back to the presentation. Now that I've shown you that quick demonstration on how to move a model from desktop simulation to real-time simulation and testing with Simulink Real-Time, I would like to pass the screen over to Patrick to talk more about the second element of this solution, the hardware. Patrick?
Thank you, Ethan. The MathWorks Speedgoat fully integrated real-time testing environment is formed by Simulink Real-Time software and Speedgoat real-time target machines. So let's discuss the hardware portion of our solution in more detail. Speedgoat is an associate company of the MathWorks and provides tailored turnkey hardware solutions ready to use out of the box. After discussing your project-specific requirements by phone, email, or on-site, Speedgoat will provide you with a solution proposal for a ready-to-use configuration tailored to your performance, I/O, and protocol interface requirements. The delivery typically includes the real-time target machine with I/O modules installed and cables and terminal boards to easily access all available physical I/O lines. The driver library included with the delivery extends Simulink Real-Time with the necessary driver blocks required to interface with all I/O and protocol interfaces. Last but not least, a test model serves as an example in order to immediately get started with the solution. Simulink Real-Time and Speedgoat target computer hardware are expressly designed to work together. The Speedgoat platforms are modular, flexible, powerful, and cost-effective, and over 300 I/O modules are available, supporting an extensive range of I/O and protocol interfaces. The performance real-time target machine is the ideal choice for office and lab use. It leverages latest generation Intel i7 CPUs and optional Xilinx FPGA technology to execute real-time applications on multiple cores, target machines, and FPGAs. The flexible expansion concept allows more than 50 I/O modules to be installed, and flexible mounting options allow rack and desk installation with either rear or front I/O access. The education real-time target machine is offered exclusively to academic customers at a most attractive price tag. This system provides researchers, professors, and students a turnkey real-time simulation and testing environment and allows students to become familiar with solutions currently used in the industry. And last but not least, the machine we are using in today's demonstration is this industrial computer. The mobile real-time target machine provides high performance in a compact form factor. Its rugged, fanless design and the extended temperature range support makes this shock and vibration-proof machine an ideal choice for in-vehicle and other mobile applications. The flexible I/O expansion concept supports multiple I/O layers, so up to 12 modules can possibly be installed into one single enclosure. Furthermore, this solution comes with a standalone operation mode, so it is possible to run your controller algorithms on the Speedgoat hardware independent of the development computer and completely royalty-free. You can as well run Simulink Real-Time Explorer in standalone mode or leverage C and C# programming interfaces to instrument the real-time application. Speedgoat continuously expands its portfolio of target machines. End of the year 2015, Speedgoat is going to release a new small form factor real-time target machine as an addition to the mobile platform. This new system as well will be ideal for embedded production use because of its small footprint. Okay, so now let's apply this freshly acquired knowledge of real-time simulation and testing to a real problem. I'm going to hand the screen back off to Ethan to introduce our today's case study.
Thanks, Patrick. As we showed at the very beginning of our presentation, our primary demonstration is going to be controlling a permanent magnet synchronous motor. While Brad is preparing to show you how he was able to build up to that first demonstration, I thought it would be good to take a quick look at the theory behind controlling the motor first. In this section, we'll be looking to control a permanent magnet synchronous machine, which is often referred to as a brushless motor. So for those that aren't in this motor control domain, here's a brief explanation of a brushless motor. The common DC or brushed motor has commutation done internally via mechanical contacts or brushes. The brushes are the parts that are sliding right here, shown in the top. As the motor turns, the brushes supply different windings to continue the motor rotation. It is a simple design to control. Apply a voltage and the motor spins. There are two simple equations that relate current, voltage, speed, and torque. The brushless motor is more efficient as it doesn't have these lossy, messy mechanical brushes, but the trade-off is that the commutation must now be done by electronic commutation. This is typically through the use of a microcontroller running some sort of feedback loop algorithm. In our case today, the feedback comes from a position sensor attached to the motor, and that feedback will be used by an inner loop to control current at 10 kHz and an outer loop to control motor speed at 200 Hz. I might point out that we have a version of this control running on a performance target machine at 50 kHz. At this highest level, we have our host running Simulink connected via a network cable to our real-time controller. The motor is driven by a 3-phase power driver board, and its shaft has mounted on it an incremental encoder. The power electronics may be something that your company designs or builds or subcontracts, or it may be a commercial off-the-shelf hardware. In today's example, we've chosen to use commercial off-the-shelf hardware. Specifically, we are using a TI DRV8312 integrated circuit. This brushless motor driver chip is available from TI on a low-cost development board. It's shown here with the included motor and 24-volt power supply. You can also see here that there is a microcontroller module, but we've removed that today for the rapid prototyping demonstration, as we'll be using our Simulink model with Simulink Real-Time as the motor controller. The TI driver board includes a header to access the board signals. With the help of our hardware engineers at Speedgoat, we created a shield so that we could interface with the standard I/O connections from our cables to our motor electronics. Again, for your application, the power electronics may be something that your company designs and builds or subcontracts, or it may be COTS hardware such as this, or something more productized. Here's a simple view into our power electronics. Our controller will be varying the voltage across 3 motor phases using PWM techniques. Our real-time target computer will provide these 3 PWM signals to drive each of the 3 half bridges on the driver chip. For feedback, the TI board provides current sensing circuitry for us to acquire our current measurements. We also use an optical encoder to determine the motor position and velocity. There's a small but critical point I'd like to point out about synchronization. For those not familiar with PWM, these signals are either high or low. So either the top or the bottom transistor of each bridge is on at any given time. Now, take a look at the current measurement points. These points have current flowing through them only when the lower transistors are on. The key point to remember is that we're not free to sample the current whenever we'd like. Instead, we'll have to synchronize the control signals with the feedback signals. This timing diagram shows the challenge of getting all the synchronizations correct. The PWM signals have to be synchronized with each other, as this provides us with a window of time when the currents can be measured. The good news is that our mobile real-time target machine is configured easily to do this. In a moment, Brad is going to demonstrate how we experimented creating the PWM and PWM triggers to get the best performance out of our motor. But before I hand you off to him, let's take a closer look at how the mobile real-time target machine is connected to the hardware setup. For today's application, we are using 3 PWM output channels and 3 signals dedicated to the incremental encoder attached to a digital input and output module. Then, there are 2 analog input channels for current measurements attached to an analog input module. These modules are attached to my IO331 FPGA card, which sits on the PCI bus of the target computer. While Speedgoat provides fully capable I/O blocks for each of these I/Os, we needed to have more control over the PWM algorithm at first to understand how to control our motor. We took advantage of being able to target our own algorithms onto the Speedgoat FPGA through Simulink, and Brad is going to show you that exercise right now.
Sure, Ethan, no problem. So to implement the PWM algorithm that Ethan mentioned, we always start in simulation. So I created this model, and here I have the PWM component, and this is where I express the behavior I want out of this component. So let's take a look at it. If I go inside, you can see I have state machine here. This is going to implement my up-down counter, which is going to generate my PWM carrier wave. And this is implemented in state flow. If I look inside, what you'll notice is I have 3 states. I have an init state, and then I have a count up and a count down state. And so once it starts running, it's just going to keep cycling through, counting up, counting down, ad infinitum. Back up here to this level, what's happening is I have basically a duty cycle command coming in here on this port, and this logic over here will take care of generating the correct edges on my PWM digital outputs to implement the duty cycle that I'm requesting, 30, 40%, whatever it may be. And finally, the logic up here is how I implement my triggers. So right now I'm starting with just a single trigger. This is where we began. We also might want to experiment by adding additional triggers at different points in the PWM period, and if I did that, I would just add some additional logic up here to get that working. So just a little bit about the algorithm itself. I'll back up to the top level. So having implemented this in simulation, of course, I want to run a test and see if it works correctly. So let me do that now. I'll hit the play button. There's an oscilloscope here that's looking at those PWM signals coming out of my subsystem. And let's take a look here. I'll zoom in on a few of these, and let's just see what we get. Okay. So let's take a look at the first one, PWM-A. That's this guy up here. I was commanding, as you see in my system model, 10 microseconds, and that's what I got. 10 microseconds. It's a smidge off because I do have some integer math going on inside of the PWM algorithm, so I have a bit of rounding. Also notice that I have a 10 kilohertz period. That's the frequency, and so that's also per my spec, so I'm happy with that. If I want to go down here and check PWM-B, for example, I'm getting 20 microseconds, and that's what I asked for. You can see here 20, and then if I check PWM-C, I'm expecting 30, and that's in fact what I get. So good. At this point, I have a functional design. It's behaving the way I specified. So what I want to do now is actually implement this on the FPGA itself, so I can check it in hardware and see if it behaves the same way. So the way I do that is to implement just the part you see here in this subsystem. So I'm going to invoke a tool by right-clicking and going up here to the HDL Code menu and invoke what's called HDL Workflow Advisor. So I'll click that. That's going to bring up a tool that's going to guide me through the process of generating HDL code from this model. So what you see here in the tool as it's opened up, I have some parameters that it's asking me to specify. For example, what board. In this case, we're using a Speedgoat IO331 board. What synthesis tool? And we're using the Xilinx. It's a Xilinx part, so we use their ISC tool. I need to then specify the target interface. What this is the mapping of the ports in my design subsystem, my PWM component model, to the actual hardware pins on the FPGA. For example, this top port is a PCI port, so that's a connection between the CPU and the FPGA, so I specify it as a PCI interface, and it automatically configures an address register for me. So having specified all the different pin mappings to my ports on my design, last thing I would do is specify the clock frequency of the FPGA itself. Here I'm using 75 megahertz. And then once having done that, I would go up to the top and right-click and say Run All. And what that would do then is it would run through checks in the second stage to make sure the model had the proper configuration to support HDL code generation. It would actually then generate the HDL code, invoke the synthesis tools, the Xilinx tools, to generate the programming file and then get that file ready for downloading. It turns out for this particular design, it takes 5 or 6 minutes for this to finish. So rather than make you sit through that, I'm just going to show you what comes out at the other end after the build process is complete. So let me do that. So let me pick up the output. So what it will do is generate this model. As you can see, it's basically a replica. It's a copy of the test bench model I was using to do my design just in simulation. So this stuff is all the same, but what's different is my PWM component subsystem has been replaced with a what's called an FPGA interface module. And this block contains all the information necessary to program the FPGA, and if there's any interfaces to the CPU, that would also be specified. And in my case, I have these two ports. I'm sending two signals from the CPU down to the FPGA. Also what it did, it left the output ports that I had in my original design, which actually got mapped to the FPGA pins. Those are now stubbed out because they're actually connected to hardware pins, so I don't need them to be present in this interface module anymore. So what we typically will do is, just to clean this up, we'll run a little script that'll go and strip these out. And when I do that, I get a model that looks like this. Same thing as you just saw, but now I just cleaned out all those stubbed out ports and I just have the ones I really need to actually execute the design. So now I'm ready basically to test this on the hardware. So what I'll do to actually make that happen is, as I did in the beginning, I'll hit the build button here. So I'll click that and the build process is going to initiate, and let's kind of scrunch this up here a little bit so you can see the progress. So what's going on is the code generators has been invoked. It's generating C code for this entire model. It's also picking up a couple of things from this interface block. I mentioned that it has everything necessary to program it. One of those things is it specifies the FPGA programming file, which we call a bitstream file. So as part of this build process that I've initiated, not only will C code be generated to program the CPU, but the appropriate FPGA bitstream file will be automatically downloaded and used to program the FPGA, and that happens for me automatically. So just a quick check to see if that's complete. It is. Okay. So now I have built and downloaded the application. It's ready for me to interact with it on the hardware. So the way I'm going to do that is I've put this model in what's called external mode. It's a feature of Simulink. So this allows me to actually control the application on the real-time target from my Simulink model itself. So the way I do that is I click this Connect to Target button, and this is going to connect my Simulink model. Now you can think of it as just a kind of an interface front end to the application that's on the target. Now when I hit this play button, what you should see is signals appear on the scope, which would indicate that the algorithm is actually running and the PWM is generating output pulses that I can actually measure with an oscilloscope. So let's do that. So there it goes. Okay, so what you're seeing is, and let me kind of point out a couple of things in my hardware setup. You may notice a couple differences from the one earlier. First big thing is I've got an oscilloscope now and I don't have the motor. Because I'm actually testing just the PWM peripheral by itself with no actual closed loop control, I took the motor out of the circuit because I didn't want to inadvertently damage it. I have the scope connected via these probes to an interface board, which is connecting my Speedgoat real-time system to the power electronics board. And there are some test points on this board which allows me to sense the PWM signals, among others. And that's what I'm displaying for you on the oscilloscope right now. Okay. Another thing I can do from this external mode is I can actually interact and tune things live. So for example, I'm requesting 10 microseconds pulse width on my A channel. I can double click this and change it to, I don't know, 30, let's say. And you'll notice on the scope that the pulse width changed. So that's what I want to see. That tells me that I have this live interaction. It's functioning. It's responding to my commands. So that's good. So let me now put him back to where I had it at 10. Okay. Next thing I want to do is verify on the scope if the pulse widths are as I specified. In my case, 10, 20, and 30 microseconds. So I'll do that by moving some cursors and measuring the this pulse width here. So let me turn those on. I've got that. Let me grab the left cursor, and I'll put him right on that edge. It's about there. And let me grab the left cursor. And what I'm doing is I'm going to move him over and measure the right edge of that pulse. And as you can see, oops, let me get it right there. And I look over on the scope and I see my delta X. Exactly 10 microseconds. Perfect. That one checks out. Let's do the channel B just for for kicks here. I'm moving the left cursor to the, sorry, the right cursor, I mean, to the right edge, and I'll grab the left cursor. Let's move him back, and I'm grabbing then the other edge. Let's see if I can get him lined up. There. Okay. So given my visual acuity, it's saying 19.8, so basically 20 microseconds there. So that's looking correct. And then just for completeness, I'll get the last channel, which I expect to be 30. Let's get this guy. I'll move this edge over here. And there. Yep, 30 microseconds. Great. I'm happy with that result. This tells me I have a design that's working, it's functional, and so I'm basically, at this point, ready to move forward and take my next step. And so the next thing I'd like to show is the full closed-loop setup with all of my peripherals implemented on the target machine, and that's so I can then test the motor control algorithm itself. But in order to do that, I'm going to need to reconfigure my test setup here. I need to disconnect the oscilloscope and then reconnect the motors. So while I'm doing that, I'm going to pass you on to Patrick for a few moments, who's going to talk a little bit more about the FPGA technology that I just showed.
Thank you, Brad, for the demonstration. This demo leverages a powerful FPGA-based I/O module for PWM generation and encoder capture. Megahertz granularity is needed to adequately cope with PWM and encoder signals, and the FPGA is the perfect candidate for this task. The card used offers digital and analog I/O connectivity and is therefore ideal for motor control applications. You can do the PWM and encoder implementation yourself, like what you just saw in the demo, or you could simply leverage Speedgoat's pre-configured code modules, which are available as building blocks. Dedicated driver blocks provide direct access from the Simulink model, and no HDL coder is required in this case. Based on HDL Coder, you could consider to even run the entire motor model algorithms on the FPGA and achieve much faster closed-loop sample rates. Last but not least, it is possible to write and implement your own HDL code into the Simulink Real-Time environment by leveraging Speedgoat's FPGA engineering kits. All those workflows are based on the same hardware. So as shown in the demo, HDL Workflow Advisor allows seamless deployment of Simulink algorithms onto the FPGA I/O card. It is possible to execute algorithms directly on the FPGA instead of the CPU. Since all analog and digital connectivity is tied directly to the FPGA card, the PCI bus interface is bypassed and much higher closed-loop sample rates, up to several megahertz, can be achieved. The field-oriented controller model that is used in today's webinar is as well available in fixed-point representation and therefore ready for use with HDL Workflow Advisor. MathWorks and Speedgoat development teams have a major focus on further leveraging FPGA-based technology out of Simulink. As an example, Speedgoat just released the new iOS 322 I/O module with analog and digital, as well as multi-gigabit transceiver support. Additional I/O modules based on Xilinx Artix and Kintex technology are underway and will be available within the next few months. In order to further scale up this solution, it will soon be possible to interconnect multiple FPGA cards within one or multiple systems via multi-gigabit transceivers. We leverage the fast serial Aurora protocol for this purpose. All new Speedgoat FPGA cards by default have onboard MGT support, and the performance and mobile target machines have default integration of the necessary physical connections. MathWorks as well continuously invests in adding more functionality to HDL Coder. This workflow is 100% integrated into the Simulink Real-Time environment and available with a single button click. I now would like to hand over to Brad for the live demonstration of the closed-loop motor control model.
Thanks, Patrick. So let's recap. What we were talking about previously was building, testing, and validating our individual peripherals that we needed for our application. So we showed an example of building the PWM peripheral. We use similar techniques to build, validate, and test our other peripherals. And now, when we had those models completed, we rolled them back in and bolted them together, if you will, into a complete closed loop system model, which is what I'm showing you here on the screen. So once we had done that, of course, we ran additional simulations with all the pieces in play to make sure everything was working correctly. When we'd done that and had results we thought were acceptable, then of course we were anxious to try it out on hardware, so we used our rapid prototyping system using Simulink Real-Time and our Speedgoat real-time computer and started running tests. And what we found is that on our initial testing, the results were not quite as good as we had hoped. We encountered some issues that we didn't anticipate, and so but basically that's what rapid prototyping helps you. That's why it's there. So we're able to use the data logging capabilities that it provided to identify and troubleshoot the issues, figure out a root cause, and then go back to the simulation models, make appropriate updates, and then to get the simulation results to match what we were seeing on hardware. And when we did that a few times. We'd change the model to make it match, then retest it on hardware, get further, maybe encounter some other thing that we didn't anticipate again. Same process. Identify it using the data logging, and then go back, update the model. And we did that a few times, and finally we got to a point where everything was working very nicely. We were very happy with it. So then we were ready to move on. So let me just show you a bit about how how I did these iterations, just to remind you. So what we would do is, before I jump to the next model, remember the controller. This is the piece that's going to be common. So this controller element here is going to be retained. So I'm going to pop you into the model we used to test on the rapid prototyping system. So here's our controller in the center. And as you recall, this is the same model I used at the beginning of our talk, where the plant model is replaced by these I/O driver blocks that I've colored orange here to make them kind of stand out. And these blocks are what allow me to connect the input and output signals in our controller to the I/O card that's in our rapid prototyping system here, and that's where the peripherals are implemented, and then they in turn are connected by these cables to the inverter and the motor itself. Another thing to point out, you may be wondering, for example, here's this block for PWM and it says Speedgoat PWM, but previously I just showed a custom PWM implementation using HDL Coder and the HDL Workflow Advisor. So the reason that I showed you that is in the beginning, when we were developing the application, we wanted to experiment with different kinds of PWM implementations, and specifically we were looking at triggering. Where would we have the trigger? How many would we have? Things like that. So we wanted freedom to try different things out. So we used the HDL Coder approach. After doing some of those tests, we came up with a specific configuration we liked. Then we looked at what Speedgoat had, and their PWM implementation had more than enough functionality to cover what we needed. So we thought, well, we wanted to leverage their implementation rather than having to maintain our own. So we just opted to use theirs. So that's where that came from. Okay, so with these I/O driver subsystem blocks appropriately connected to my controller, to get it on hardware, I click on my Build Model button, and again, what will happen is that will invoke the code generator. It's going to build C code for my controller model here and compile it. It's then going to link in the application, or I should say the existing code for my I/O driver modules, and then convert that into an executable and download it via this Ethernet cable here from my host computer to my real-time target computer here. Let's see if I'm going to check the diagnostics and see if it's completed. Looks like it's still building, so I'll let it go just a little bit longer. Okay, So now we have a complete build. It's downloaded onto the target and it's ready to run. So we'll get rid of this. So what I'm going to do next is what I did again in the beginning. So let me go back to MATLAB. I have a script here that I'm going to run that's going to execute a test for me. So let me just run through that. So what this will do is it will set up some data logging for me, actually initiate the test. As you can see, the motor is spinning. Once the test is complete, it's going to upload that data and display it for me in a data visualization tool called Simulation Data Inspector. It's just a capability that ships with Simulink. So what I would do, what I always did when I was looking at tests like this, is I would usually pick on the rotor velocity signal first. So let's see what that looks like. Yep. And this is what I expect to see. I was doing a step response test, so that's the response I was looking for. I may want to look at other signals, so I can go in here and reformat my layout here and add another plot window, for example. Maybe I'll put some phase currents down there, maybe the A and the B phase currents, and I'll zoom in a little bit and take a look here and look at the results. And again, I see, you know, what I'm expecting, nothing unusual. Pretty happy with how this looks. So what you've just seen is an example of me interacting with the system in an automated way, a scripted way. And that's very nice if you have a whole lot of tests. Maybe you have a regression test suite, a collection of tests that you like to run. So every time you make a design iteration, you'd like to be able to run a battery of tests to make sure everything is still working. So it would be very nice to be able to automate that, and so you can do that. In fact, that's what I was doing with this test I just ran, is I'm leveraging the MATLAB API that comes with Simulink Real-Time to automate my interactions. And so you can do that, and we do that quite frequently in our design work here. So that's a handy thing. But what if, after running regression tests and you have a design you're comfortable with, what if you want to control your application interactively? What if you want to just do something where, hey, what if I try this, or what if I try that, and observe the results without having to resort to crafting up scripts? So there is a way of doing that. Actually more than one, but one common way is to use a tool that ships with Simulink Real-Time. It's called Simulink Real-Time Explorer. So let me open that up for you. The way I do is I just type from the command line Simulink Real-Time EXPLR, and that will pop up the window. Okay, so the tool is opened up now, so I can take a look at it. So it's got this big blank area where you can arrange different views of signals, parameters, things like that. I've actually got a layout that you can save layouts. I've built one and saved it, so I'm going to bring that in now so you can see it, just to save a little time. So I'll go up here to File, Restore Layout. I'll go select it here. Okay, and what you can see here is I've got some signals that I previously was monitoring, and I have this what's called an instrument panel that I created down here. This is a very common way for you to make essentially like a user interface for an application, something I like to do, especially to make it easier for me to interact with the application on the real-time system. And the way you build these is you go up here to this palette, which has a collection of, you could call them widgets, but they're basically controls, knobs, sliders, gauges, things like that, that I can click and drag onto this canvas here to construct an instrument panel. So I've done that previously, so I've got an on-off button here to control the motor. I've got a gauge here for the angular velocity of the motor, and so once I have that control dropped onto my canvas, then what I want to do is connect it to, in this case, the rotor velocity signal, so I can monitor it. So I'd go up here to my list of signals, and here I have the rotor velocity signal. I would just left-click, drag, and I would just drop it on here, and that would make the connection for me, and I'd be ready to go. Same operation for control widgets that are associated with parameters, like this on-off button. There's a parameter in my algorithm that's the motor on-off switch, and then I would drag that parameter on here, and I'd be ready to go. So now that I've got this sort of laid out, let me show you how this runs. Let me run it actually and So the way I do that is I go over here to the application area. This is how a feature of the tool that allows me to control the operation of the application on the real-time computer. So what I'm going to do here is hit the Start button, and that starts the application running on the real-time system. I'll then start my panel, my instrument panel, and now that that's going, I can go and, for example, I can turn the motor on. So I'll click that, and now you should see the motor spinning here on the screen. Once it's going, you also notice that the gauge is displaying the target speed, or the actual speed, I should say. I can control the target speed here by this little slider. So I'm dragging it up, and you'll notice it's going faster, and of course I can slow it down, things of that nature. And then if I want, I can turn it off by clicking this button, and you'll see it slowing down, coming to a rest, and finally, and the gauge running there, I can turn it back on again. So just an example of one of the ways I've set up kind of a interactive session with my application using the Simulink Real-Time Explorer tool. So what I've just shown you is a sort of a scripted and interactive way of controlling an application in the rapid prototyping system. And for us, the key benefit of using or integrating the rapid prototyping into our development cycle was that we could find and fix issues early in the design cycle. And this is especially important if you don't have access to your production embedded control system or embedded system that you're going to ship to customers. If that's the case, you don't want to be in a situation where you've got an algorithm developed, but you've never tested it on hardware, and then when you get your turn on the embedded, the production embedded system, when it shows up, you have a really tight deadline, and you're trying to troubleshoot issues, and you don't want to have those things pop up there. You'd like to have done a bunch of pre-work, which you can do with a rapid prototyping system, to find and fix issues ahead of time. The rapid prototyping system makes it very easy for you to see and log internal signals of your application and quickly turn around design iterations. So for us, that was a huge benefit. At this point, because I've been able to use a combination of simulation and the rapid prototyping to verify my design on hardware, I've got a lot of confidence that this motor control application is going to be successful, and I would be now wanting to take the next step, which would be to migrate my design into a production implementation. But that's a whole other conversation beyond the scope of our talk today. But if you're interested in that topic, we do have a webinar on our website that deals with it. And there'll be a link in the slides that Ethan will cover in our wrap-up where you can go and access that. So with that, I'll hand it back over to Ethan, who will kind of wrap things up for us and conclude the presentation.
Thanks, Brad. I hope you enjoyed the demonstration and got a better understanding of what rapid control prototyping is. Also, we hope you were able to see the versatility that Simulink Real-Time with Speedgoat hardware is able to provide for rapid prototyping. There are a few next step slides that we'd like to present.
We offer tailored hardware for your application, along with hardware warranty and maintenance services. All hardware components are available for a long period of time, typically 7 or more years. And of course, MathWorks and Speedgoat provide professional technical support for the complete real-time testing solution. If you're interested in learning more about the capabilities of this solution, feel free to contact us directly. We are happy to have a conversation with you about your project specifics and assist you in finding an appropriate system configuration.
Thanks, Patrick. Just a few additional links that highlight examples in this area. The second one is that webinar that Brad pointed out that begins where we left off today. We're recording this presentation, so don't feel like you need to hurry up and copy down all the links. We will be sending a follow-up email with the link to the recording in about a week or so. You can grab them all then. If you can't wait, please don't hesitate to contact us directly through the MathWorks website. We would be glad to assist you. Thank you again for joining us, and we'll see you soon.